Good morning to one and all. I am Parthiban working as assistant professor in the Department of ECE, Sri Muthukumar Institute of Technology, Mangadu, Chennai. Now I am going to talk about the subject called electron devices, which is coming under the regulation R 2025. The subject code is EC25C01. Particularly, I am going to talk about the unit 1, in which we are going to see about the carrier generation and recombination mechanisms. So the recombination lifetime as well as about the surface recombination as well as about the photon generation. Generally these are important because they form the basis for understanding of semiconductor diodes, transistors as well as solar cells and also about LEDs as well as photodetectors. So for understanding purpose we are going to see about the light with photon energy. Here the HV should be less than that EG. HV is nothing but the photon energy which will be generally less than the energy band. So it is a convenient expression for energy of a light. So light with energy should be HV should be greater than EG when it is absorbed with the unabsorbed light intensity as a function of depth as depicted in the semiconductor. So the semiconductor as well as for other materials which has been classified in the diagram very clearly. So from the diagram we can see the generation mechanism that is called band to band generation, which is also called as direct generation. In semiconductors, the electrons exist in the valence band under normal conditions. When sufficient energy is supplied, an electron can jump from valence band to the conduction band. The energy can come from the form of thermal or it can be from light energy. When the electron moves to the conduction band, but it leaves behind a hole in the valence band, this creates electron hole pair. This mechanism is very important in deciding the characteristics of intrinsic concentration. It forms the basis for solar cells as well as for photodetectors. It enables optical absorption even in the indirect band gap materials like silicon, which can also undergo this process. This is the very fundamental carrier generation mechanism in semiconductors. Then coming on to the generation via recombination and electron hole pairs, we can see in real semiconductors the defects and impurities will always exist. These defects induce energy levels that will inside the band gap that is called trap levels. So the first step, an electron from the valence band moves into the trap level, creating an hole in the valence band. In secondly, the trapped electrons gains energy and moves into the conduction band. As a result, the electron hole pairs are generated. However, this mechanism is totally undesirable because it is caused by defects. It reduces the device performance, but also it increases the leakage current, which is totally uncalled for. So, as the aim of manufacturer is always to minimize this effect. Then coming on to the mechanism that is called impact ionization. This is clearly depicted in the diagram where we can see the direct versus indirect band gap that is occurring. So which is called the impact ionization due to the high electric field conditions. At high energy, the electron accelerates due to the electric field. These electrons collide with the atom and transfers energy. This collision breaks the covalent bond and creating a new electron hole pair. This process can repeat and create many carriers. This leads to the chain of reaction that is called avalanche multiplication. This mechanism is used in avalanche photodiodes as well as high gain detectors. This was clearly depicted in the diagram. However, excessive impact ionization can damage the device. That we have to take into account. Then coming on to the photo generation, which is occurs due to the light energy because it generates carriers. When a photon with energy greater than the band gap strikes a semiconductor, it creates an electron hole pair. This generation rate depends on the absorption coefficient and penetration depth. If the absorption is low, then the carriers are generated deeper in the material. If the absorption is high, the carriers are generated near the surface. This principle was very much used in the solar cells as well as in photodiodes as well as in optical sensors. The photo generation is a very key operating principle for optoelectron devices. In the diagram, we can see the direct band gap as well as indirect band gap materials. So, the direct band gap, we can see there exists the recombination effect directly. In the indirect band gap, there exists the recombination effect by means of a, we can say, a subtended angle, or it can be via a cross structure. So the direct bandgap material examples are gallium arsenide and its compounds. The example for indirect bandgap materials are silicon germanium. So in the direct bandgap material, there is a possibility of the carrier recombination. Because of this, the emission of light is occurring. The typical example is LED. In the indirect band gap is a typical example for ordinary diode where there is a conduction takes place but there is no emission of light. So in the next diagram we are going to see the relationship between the direct versus indirect band gap variations. Now the N naught and P naught represents the equilibrium of electron and hole concentration, whereas the N and P represents the carrier concentration under external conditions. The delta N and delta P represents the excess carriers. These excess carriers may be a positive or negative. The total concentration is N equals equilibrium plus excess carriers. Similarly, for holes, under non-equilibrium conditions, the carrier concentration changes due to external excitation. Low level injection means excess carriers are much smaller than the equilibrium carriers. This condition is very important in most device analysis. From the diagram we can see the magnitude of electric field of a photon of a light. So for the polar materials we can see like gallium arsenide, indium phosphonate as well as gallium nitrate. This tends to be better at the absorbing light. So the electric field resonates with atomic dipole and it is absorbed very strongly. So in the next diagram we are going to see about the three methods of recombination as well as three methods of generation mechanisms in diode. So the electron emission occurs when a trapped electron gains energy and moves back into the conduction band. The capture rate generally depends on the carrier velocity, the trap velocity as well as the capture cross section. This mechanism is dominant in defective materials. So the recombination as well as the generation methods are very important. There are three famous mechanisms for recombination. One is called the SRH recombination method. Shaker-Reed-Hall recombination method is also called. The next one is called radiative recombination method. The third one is called Auger recombination method. So the total lifetime is given by 1 divided by the total lifetime, that equals the sum of inverse of individual lifetimes. So at low carrier concentration SRH dominates, at high concentration Auger recombination dominates. So the carrier lifetime defines or determines the device performance. So with that I am winding up the lecture. In the next lecture we are going to see about the recombination mechanisms. It is also having three types as well as the basics. So these are the references that I used to have. Thanking you one and all. Thanking you.